Hi, so we're going to get started with chapters 2 and sections 2.1 through 2.4 today. An element is a pure substance. We've gone over that before. But each element is identified by a 1 or 2 letter symbol. If it's 2 letters, the first letter is always capitalized, but not the second letter. So make sure that if you're writing your chemical symbols for an element, that you have the first letter capitalized, but the second letter, if there is a second letter, needs to be lowercase. So for example, chlorine is Cl with a lowercase l, not Ci with an uppercase I, even though uppercase I and lowercase l do look similar. You'll see me write chlorine as C with this little loopy lowercase l, so I don't confuse it with Cl, which could be an uppercase I. I always also write my uppercase I's as with serifs with little N's on them, and that is helpful. The elements are arranged on the periodic table. You have a periodic table for this class, so please make sure you're using that for homework and as you study so you're familiar with it. And then the position of the element on the periodic table can tell us a lot about the chemical properties, and we're going to talk about this in this chapter. So there are some common elements and their symbols. You're going to see your memorization. See the memorization list in D2L for the element names and symbols that you need to memorize. And then make some flashcards, maybe with the element name on one side and the symbol on the other side. And here's an example of the periodic table. So the periodic table is divided into 3 sections: metals, nonmetals, and metalloids. Metals are located on the left side of the periodic table. So if we look at this one, the metals are in green. That's going to be everything kind of on the left side of this zigzag. There's a little stair step here. Everything on the left side of that stair step is going to be metals, except for hydrogen. Hydrogen's a little bit different. It's going to be a non-metal, and you can imagine hydrogen maybe used to be right here, but it moved over here because it has similar properties sometimes to these elements, but also sometimes to these elements. Metals are good conductors of heat and electricity. You know that we use metals for electrical wires like copper. We also use metals to conduct heat, like in cooking with like an aluminum pan. And they're usually shiny solids when they're at room temperature, except for mercury, which is a liquid. So that all metals are solids except for mercury, Hg, which is a liquid. The next category is going to be nonmetals. These are on the right side of the periodic table. So if we go back to this periodic table, we're looking for nonmetals in blue. So they're on the right side of that stair step line. And then you also need to add hydrogen to that family, to that group. They usually have a dull appearance if you do see them as a solid. They're usually poor conductors of heat and electricity, but they are solids, liquids, or gases. So you have some solids. Carbon and sulfur are examples of some solids. You've got one liquid, bromine, and then you've got gases like nitrogen and oxygen. All of this family here are also gases, and hydrogen is a gas. Nitrogen is a gas, oxygen's a gas, fluorine is a gas, chlorine is a gas, bromine is a liquid, and then carbon, phosphorus, sulfur, selenium, and iodine are solids. And acetylene is also a solid. Then we have metalloids. Metalloids are located on the line, except for aluminum. Aluminum is pretty metallic. So if you see if it's touching the line, except for aluminum, we would consider it a metalloid. And then when we get down here, the properties get a little weird because they're very heavy elements and probably radioactive. So we kind of stop our line here. So these are going to be metalloids, and they have special characteristics of both metals and nonmetals. So they're kind of in between them. So you have your 6 metalloids here. You can see based on where they are on the periodic table why they're kind of in the middle. So just a quick little connection to the human body. There are 4 elements that make up 96% of the mass of the human body: carbon, hydrogen, oxygen, nitrogen. Organic chemistry, which you'll take next semester in 1152, focuses mostly on these elements. They make proteins, carbohydrates, lipids, nucleic acids. They all contain these elements. We also have other elements in the human body, major minerals like magnesium and sulfur. These are found in proteins. We need these. And then we have trace elements like iodine, zinc. So you can kind of see a list here of some major minerals, trace elements, and the building block elements, and just to connect it to some real life stuff. A compound is two or more elements coming together. And so chemical symbols will show us how to do the compound. So write the element symbol, and then we write the subscript to show how many elements of that chemical. So if we have H2O, this is telling us, the 2 is telling us about the thing right in front of it. So 2 hydrogens and 1 oxygen make water, which is H2O. If we have C3H8, we know there are 3 C's and 8 H's, and that makes something called propane. You can draw compounds in different ways. You'll see in this book that we draw them in this space filling model because that's kind of more what we think they actually look like. You also may see ball and stick models, and this is just the representation that we would maybe write on paper. And different elements are represented by different colors. So be familiar, I think, with these colors because they're going to be used most often. But again, on the test, it's going to be black and white, so you don't have to worry about this kind of stuff, but you may see these models used in ALEKS and in the textbook. So the structure of an atom has, there's 3 different parts in the atom, 3 subatomic particles that we'll talk about, protons, neutrons, and electrons. The charge of a proton is +1, the charge of a neutron is neutral, 0, and the charge of an electron is -1. So because of that, I like to write protons as P+, neutrons as N0, and electrons as E-. You don't need to memorize the masses of them in grams. We do look at the masses in AMU, or atomic mass unit. So AMU represents atomic mass unit. And we're trying to make our lives simple by saying, hey, what if we call this number here about 1, right? If this number is about 1, because this is about 4 decimal places off, we're going to say that's pretty much 0. So do electrons have mass? Yes, they do have mass, but it's so small in comparison that we're just going to say the mass is 0. So when we're counting up the mass of the atom, we're only going to count the protons and the neutrons. So we can see here the mass consists of the protons and the neutrons. And if we look at the charges, the neutrons don't have anything to do with the charge. So the charge is going to be made up of the protons. I like to count protons, and I subtract the electrons. The reason I subtract electrons is because electrons have a negative charge. So we can figure out the charge of a particle by doing protons minus electrons. We can figure the mass of the particle by doing protons plus neutrons. And this is the mass in AMU. We're not really going to worry about the mass in grams. So the protons and the neutrons, they live in the center of the atom. This is called the nucleus. And it is a very, very, very small and very dense. So all of the mass is in the nucleus. There's a very small amount of mass in the electrons. And then the electrons hang out in what we call the electron cloud, kind of around the outside of the nucleus. And that comprises most of the atom's volume. So most of the mass is in the center, most of the volume is kind of around in this cloud. And the cloud is made of mostly empty space with electrons kind of scattered around. There's a great video in D2L, or I posted somewhere I think it's in D2L, about the size of an atom. So just check out, if you just Google TED Ed, how small is an atom? You'll see the video there, and it's a really great video to just get an idea of exactly how small an atom is, because it's very small. When we're talking about atomic size and atomic charges and just like what's going on inside the atom, you have to remember that opposite charges attract and like charges repel. So the protons in the center of the nucleus, the center of the atom, all repel each other because they're all positive. So that's why we need the neutrons in there to kind of hold them together. And then electrons are attracted to the protons, but they're held in this outer space by forces we won't really talk about in this class, but just to kind of know the basic of how we're going to think about things in chemistry is that positive repel for positive, negative repels negative, and opposite charges attract. So from the periodic table, if we look at the little structure on the periodic table, at the top of the element symbol, you'll see the atomic number. We call this Z for short. Atomic number is, you'll see represented as Z. I'll just probably say atomic number. So atomic number is the number of protons. And that's kind of like the ID, like your ID number. So all lithium atoms have an ID number of 3. So if you are a certain atom, you have that number of protons. So different elements have different atomic numbers, different numbers of protons. So your number of protons is really your identity. And then if you want to think about number of electrons, if you have a neutral atom with no charge, number of protons and number of electrons are equal, but only with a neutral atom. If you have a charge, then your protons and electrons are not equal, only in neutral. We will assume always that we're talking about neutral atoms before we talk about charges. So only if you're told there's specifically a charge will you assume that these two numbers of particles are different. And so just a summary of what we talked about, protons and neutrons are in the nucleus, then we have electrons kind of hanging out in the cloud. If we look at this box in the periodic table, we see the atomic number, for example, lithium is 3, which means we're going to have 3 protons. Then we'll have 3 electrons, assuming that it's neutral. We'll talk about the neutrons in just a moment. The atomic weight is the weighted average. So this number we see on the bottom of the periodic table square is the weighted average of all the different masses of what we call isotopes. So isotope means same place. Iso meaning same, tope meaning place. Same place in the periodic table, so it's the same element. But they have different masses. And so we can think about what that means for their particles. So same element means it's going to be the same number of protons. Different masses means it's going to be different number of neutrons. So an isotope, if I say like, oh, there's 4 isotopes of lead, that means that they all have the same number of protons, but they have different number of neutrons. They'll have different masses. Well, you see this number here, this is the average, weighted average of all those different masses for the different versions of that element. We will use this kind of as our guide for the weight. You can just round to the nearest whole number to get an average mass. So the periodic table is divided into groups, which are columns, and periods, which are the rows. So main group elements are the tall columns. We number them 1A to 8A, or 1 through 8, or 1 through 18, or 1, 2, and then 13, 14, 15, 16, 17, 18. Depends on what you're looking at. If your periodic table maybe uses A's and B's, or just kind of go straight across. And there are 10 short columns in the middle. We call those the transition metal elements. And then the inner transition elements, they are that little pop-out group. There are no group numbers assigned to that. So we'll look at the periodic table to look at this. So we have our periods across, so period 1, 2, 3. Our groups are down the column. And if you look at group numbers, you'll see what I mean by 1, 2, 13, 14 through 18. These are the group numbers. Then you've got the transition elements in the middle. They have group numbers that start with B, or usually we just keep going 3 to 12. And then these are the inner transition metals. All of this group fits right here if we kind of pop it out in 3D. Okay, so that's it for this video. I'll see you in class. Have a good one.